So the bell tolls, I hear it. So let's get started. So we're on to chapter 7. So chapter 7, we did a ton, up to this point, we've done a ton of circuit analysis, right? Hopefully you feel like your circuit analysis skills have gotten a little bit better. You know, you can see things from a perspective of, you know, kind of just overall energy, right? Or how do things sort of work out with KVL and KCL? And from electrical engineering's perspective, you know, we're really just about energy and looking at how energy sort of flows through a system or is dissipated through a system and how it transfers. So, you know, hopefully you get a little bit better skill set on how to do circuit analysis. And then we introduced that fancy tool, right, Laplace, to help us solve all those equations. Because anytime we have inductors and capacitors in our systems, we're going to have to deal with things that vary in the time domain, right? So if you're taking AC circuits 112, you know, we kind of assume that everything is steady state, where a lot of the students who graduate in our program look at things from a steady state perspective, which is great. We don't have to worry about Laplace, except when you actually model real world physical systems. Just about every other discipline is going to look at things as something varying with respect to time. So a lot of analysis that we can do for mechanical, chemical, whatever different discipline you're talking about, you're going to look at things from a perspective of how do things change over time, okay? So we can generalize our approach to circuit analysis and just draw things as equations or blocks or squares. And so what that allows us to do is, if we have a very complicated system, take your cell phone for example, with however many millions of circuits are in it doing its thing, it would be almost impossible to analyze a circuit analysis problem that has up to 1 million elements. But what you can do is, if you can take a circuit and break it into smaller circuits, and as long as the interstage loading, which is the loading in between the stages that you develop, is not so significant to really change the results, you can actually model things and say, wow, well, I can just model this little piece, then I can model this little piece and this little piece until you model an entire system. And then you can put the whole system together just by tacking those pieces together, and you get a pretty good representation of how your system's going to operate. That's how engineers do a lot of detailed system analysis. It's impossible for me to know everything about every system. If I'm the world's smartest mechanical engineer or electrical engineer, there's no way I can know every little thing about every system. So I rely on an expert in that area to go ahead and do something. And then in other areas, and then we all get together and put our model together. And then we test it to see if it works. So we do simulation with a computer, that's our model. And then we actually do real world testing to see, okay, well, do I do a test, and does the result match what my simulation results are, right? Because your simulation result is only accurate or only good if it reflects what actually happens in the real world, okay? So process controls engineers, if anybody here has been thinking about going to work at a paper mill, or anything like that, where you're trying to model a process in a time domain perspective, you just say, I can't manage how does this pump integrate with this valve, which goes to this flow line, and this heater, and this heat exchanger, and yada, yada, yada. The system would be overly complex. What you do is you break it down into small chunks and pieces, and then you can analyze those systems. And so that's what we're talking about with transfer functions, is we're going to take our circuit analysis and break them down into smaller parts and then tack them onto the end. For those of you who are doing the senior project sequence currently, you're probably doing that already. You just don't realize it. So you build one part of your circuit, get that working, and then you work on another part of your circuit, get that working, and then maybe you work on a third part of your circuit, or however many parts you have, and then you interconnect them to see how the whole system responds, right? And so in the real world, there is some interstage loading that might change your results. But if you get a pretty good idea of how one part is working, and then the next part, and then the next part, when you tack them on together, you might get something that is close to realizing what your intended design is, okay? So we do it all the time. You even are doing it in senior projects. You just may not realize that that is actually what is happening, is that you're going through the process and making things easier for you, okay? So we'll do things as transfer functions, which the reason where we came up with the term transfer function is all we're doing is we're transferring the input to the output. Whatever is in the block is going to transfer whatever input signal you have. It could be a current, it could be a voltage, it could be a tank level, it could be a line flow, It could be a position. I mean, there's just about anything that you can do that you can come up with a system, and you can output that to whatever other one is. So if the tank level is your input, maybe the output might be the position of a valve on the output to either increase the flow out or in, either one, right? So you can change it so that you can maintain level. So a transfer function doesn't have to be a voltage or current in and then a voltage or current out. We do that in circuit analysis, right? That works really well for us, but it could be just about anything you want, okay? It could be a biological process, right? Everybody here, I see you working hard at the gym, getting your heart rate up, and what happens? You push a lot of weight, your heart rate goes up, right? There's a cause and effect, right? I push something heavy, that would be my input. My output is my heart rate goes up. So you can even model a lot of biological processes with a bunch of equations, except one slight problem. They aren't linear, right? A lot of biological processes do not tend to be linear systems. But has anybody been paying attention to the news? They're talking about AI doctors, essentially. You go to a doctor's office and you interface with a screen. They'll have taken some tests, blood results, whatever. You might, communicate with some sort of an AI bot of some sort, telling them what your symptoms are, and then based on test results, your heart, your blood pressure, and then maybe some of the past history, it will be able to diagnose what you have and maybe come up with a prescription, exercise more, right? If your heart rate gets too high, drop a few pounds, eat less sugar, maybe you need to go on some medicines. I mean, there could be a bunch of different things that it could do. So all that is going to be basically modeling biological processes and coming up with ways to do that. The body is one of the last bastions, right? Because it's so complex and we don't necessarily know how to do that. The other challenging part for a body is how do you test it? Anybody here want to volunteer to, let us model how a biological process happens to certain stimuli? Anybody interested? Yeah, exactly. Be pretty expensive, wouldn't it? I don't know too many people who'd be willing to do that. They do that with placebo, right? So they have certain drugs where if you have symptoms, sometimes they give you the actual drug, sometimes they give you placebo to see what the difference is. So you're sort of being a guinea pig to see if this particular drug medicine worked. But to get to that point, what have they done? They've done some animal testing, and they've gone through some simulations, and so they've done a bunch of different things to do that. So the reason why it's very difficult on the human body is because there aren't a lot of humans that are volunteering to do that. In the past, right, where depending on how far back you went, you were a prisoner of war, right? So they did tests on you to see, and it's too bad, right? And even our own government did some of those tests to do that. So the idea is that biological stuff is probably going to take a long, long time because there ain't a lot of volunteers to do that. So let's continue before we get into all this philosophical stuff. Yes?
When you meant too bad, did you mean it for prisoners of war, or did you actually mean it for like the advancing of medicine?
No, it was if I was taking the silly perspective of being the country that was holding these people captive. You don't like it, that's too bad. You know what I mean? That's what I'm not saying that that's right, but that's when they did testing on certain people and they just said, yeah, no, I don't agree with it, but that's, and they're the Geneva Convention that's supposed to, if you have prisoners of war, you're supposed to treat them with a certain level of dignity and respect. You can't torture them, and that to me would constitute torture, but I don't know. So something to think about. Don't be a prisoner of war, I guess, is the ultimate answer, If you're going to go get caught, then, take the cyanide filling that you have and, end it all or something like that. Who knows? So for transfer functions to work, we have to have a system where we can apply superposition, right? Essentially, the systems have to be linear, okay? So amplitude linearity, if we put in a system that has an x of t and we get a y of t, if we put in our system that has some sort of an amplitude increase, multiply it by 10, the output should also be 10 times y of t. So I don't even have to look at what the output is. If I initiate something that is 10 times greater than my original value, then I should get 10 times the output, all right? That's a pretty important one because that tells me this works for any signal. And superposition should apply, which means I can take x and get y, and I can take x2 and get y2, or I can put in x1 plus x2, and then I should get out y1 plus y2, right? So if I take them individually and get their outputs, and then I add them together, I should get the same outputs that I got before, right? So it's really just being able to assume that the system is linear is not going to change. So let's look at a block diagram. How many here have you taken 342? Loud and proud. Electronics 2 with John. Who's not taking electronics? Okay, that's fine. We'll go through the whole full Monty process. Make sure we're good. This is in the triangle. It's called an op-amp, an operational amplifier. And it makes your analysis quite a bit easier if you do it correctly. So an op-amp, as long as it's not saturated, okay, and we're going to assume an ideal op-amp, this connection here is a resistor, essentially a resistor. If it's an ideal op-amp, its R is equal to infinity, okay? And the other thing too is that the voltage drop between here, or minus to plus, sorry, the voltage drop here, this is Vn. The output here, if it's run on open loop, V out equals Vn times A. A is defined as my gain of my system. And if it's ideal, that's going to be equal to infinity, all right? So an ideal op has infinite input impedance, and its output is, it's basically the gain is infinitely high. So the reason why we do that is, and let's draw that back down here because I made it a little messy. We don't run an op-amp in open loop configuration. We run it in closed loop configuration, right? So we close the loop because we don't want an infinite output. So if this is V out and this is V in, this is Rn, and this is Rf, the way to analyze these circuits is to figure out the gain, the closed loop gain of the system. So we start off by saying there's a voltage in here with respect to ground, okay? That's going to draw a current into here, right? If this op-amp isn't going to be saturated, and the output here is going to be the multiple A times whatever the difference is, not V in, but V diff. So this is V diff. If A is equal to infinity, right, this is a really big number, how big should V diff be before you don't have an infinite output? If A is infinity, what should V diff be? Should essentially be 0, right? Because it's going to drive, any value that's greater than 0 is going to drive that to that value. So the voltage difference between here, plus to minus, right? Let me zoom in a little bit more. This voltage difference has to be small. In fact, has to be 0, doesn't it? If we don't want our op-amp to saturate, we want that to be 0. So the difference has to be 0. What's the voltage over here at the positive terminal? Has to be 0 volts, isn't it? Because it's connected to ground, so isn't it 0 volts? If the difference is 0 and the voltage is 0, what's the voltage here? 0. So I can determine I in as the voltage drop across the resistor divided by the resistance. Agree? So Vn minus 0 divided by Ri equals what? I in, right? That's my input current. Okay, that's step 1 to figure out how the op-amp is going to connect. Now, the other thing we said is, what is the input impedance to the op-amp if it's ideal? It's infinite, right? So if it's infinite, how much current goes inside to the op-amp? Has to be 0, doesn't it? If you have infinite amount of current, infinite amount of impedance at the op-amp, then there should be no current going into the op-amp, right? So this current has to be equal to 0. But I've got current going through here, right? This is not a 0 value. It's a non-zero value, isn't it? So where does that current go? It has to go up through here, doesn't it? That current can't go into the op amp, so it has to continue and go up through RF. So that current continues on. How do I solve for that current using RF? Well, it's the voltage drop, plus to minus in that direction, right? And the voltage drop there is 0 minus V out, right? Because we're saying plus to minus in that direction, divided by RF, correct? So what we're left with, and let's put that up over here, V in over Ri equals minus V out over RF, getting rid of all the zeros and kind of cleaning it up a little bit. So that tells me that the gain of my system, the closed loop gain, is going to be equal to V out over V in, which is equal to negative RF over Ri if you did the algebra. This is called an inverting op amp, right? Because it takes the input and inverts it because of the negative sign. So this is the gain. If I actually want to calculate what V out is equal to, I take my V in, I multiply it by negative RF over Ri, and that's how I get it. Okay? So to get my output from my input, I just multiply by negative RF over Ri. That is the inverting op amp configuration, and we do that a bunch. Questions on that? Does this look familiar to you all? Does this clean up some cobwebs or make it worse? When John does it, I would imagine John does a pretty similar approach. So, beautiful, I have an op amp, but why do I care? I can replace that as a transfer function where I run in a V of t. I go into a box and my output is V out of t. And my transfer function, which transfers the output, the input to the output, is I'm just going to take my voltage and multiply it by negative RF over Ri. So when you have a block diagram approach like this, where you just draw it as a box, you're multiplying the signal. What is better for me, though, is to actually do it in the Laplace domain. Why do I do it in the Laplace domain? Because I don't want no derivatives or integrals. This is not EET324, where that's the focus of the class. This is just going to be about doing it easier. So I have V in of S, run it through my gain, negative RF over Ri. Notice I didn't add any S's in there because I'm not taking any derivatives or integrals, right? So I'm just multiplying it by a constant, and my output is V out of S. Okay? This only applies in the real world if you're not in saturation. By the way, how can you tell if a relay is saturated? You have to look at the rail voltages, right? So if the rail voltages are plus 15 to 0, if you're pushing 13, 14 volts on your output, you're getting close to saturation, okay? So in the real world, we can't say, oh yeah, I'm going to take a 5 volt input and get a 500 volt on the output, because that probably ain't going to work too well. You can do some of that with power electronics. You know, that's a completely different, but your rail voltages had better be, 550, 600 volts, right? You would need pretty high voltages. So that's what you do when you're doing your senior projects. You pick your converters, like your AC to DC or DC to AC converters. If you want to do buck boost, you just need higher rail voltages to make it work there. A 741 op amp, the one you put on your board, it can't handle those 500 volts. But, you can get high voltage DC systems all along. Anybody here into amplifiers, car stereos, stuff like that? I look around not knowing as if I know who to look at. But the idea is that you have very high rail voltages. So if you peel back those amplifiers, some of them say warning, really high voltages, 300 volts, 400 volts, if you can crack them open. I don't know if you can, because they just use crazy high voltages to drive those. So that's how we draw that as a block diagram. This one is a 2-port network, not necessarily a block diagram. Makes it a little bit easier to do it. Questions on that?
Why are the eyes going in opposite directions?
We just typically, for block diagram purposes, just show all the currents going in. It's no big deal, right? Because if it actually is going out, we just have a negative in the number, so the current actually goes out. But typically, block diagrams, you just show everything pointing in. Excuse me. This is plus, whoops. These are always plus to minus, even if it swaps the voltage, right? Because the voltage should be the negative, so it would be the opposite. But it's okay. We just do the negative RF over RI. Sure. All right, party people, right? Did you ever look at one of these in your 342 class? Yes? Yes? Awesome, so we don't actually have to do it in this class? Good refresher. Well, we have a capacitor, right? And what does a capacitor do to voltage? Stores voltage, right? So if I want to see my equation, VC of t, what's the equation again? To get VC of t in the time domain? What is it? We've only done it about 30 times in this class. Right? We have to integrate the amount of current. Does this not look familiar? This is the generically written equation for current. So this is all well and good, except I have an integral. I don't want to integrate. I want to be lazy and do algebra. So if I take my capacitor and Laplace it, which is 1 over Cs, then my Vc of s is just equal to I of s times 1 over Cs, right? I'm not integrating anything. I'm just doing math. So if I want to make my circuit work a heck of a lot easier, why not I just replace the capacitor with 1 over Cs? Can we do the same work that we did before? Sure. This current, I in of s now, right, because we're in the Laplace domain, is going to be V in of s minus what again? 0, right, because this is a difference of what? What's the difference of voltage there between those two? 0, right? So V difference equals 0. What is another way of saying a V difference? It's a short circuit, right? The way that you make sure that there's a difference of 0 is you put a short circuit in there. But there isn't actually a short circuit because all the current would be going that way, right? So this is not a real short circuit. This is a virtual connection. It doesn't really exist. It's just a virtual connection. And the idea is that current can't flow there, but it helps give you a sense of what the voltage needs to be. Okay? So we show it as a virtual connection, but it's not really there, and that just helps us tell what the voltage is at that point. So we have our current, which again, that current has to go through here. So help me out. What is the current through the capacitor in the Laplace domain? We just did it for a resistor. What's the current in a capacitor? What's the voltage drop across here? Is there a voltage drop? Sure is, right? 0 minus V out of S divided by the impedance of the capacitor, right? Correct? So let's clean it up. V in of S over Ri equals negative Cs V out of S, right? Just by cleaning it up. And now I'm going to do my closed loop gain for this circuit, which we're going to define as V out of S over V in of S is going to be equal to negative 1 over R in times C times S, which is equal to 1 over S times negative 1 over R in times c. What did I just build there? You said you've seen it before in 342. We just did the analysis. What did we actually construct? A filter? Perhaps. A trigger? Maybe. I'm not sure how, but maybe. Here's the key. What is this? It's an integral. This, ladies and gentlemen, is an integrator. You just built an integrator. Right? 1 over s is the definition of taking an integral, is it not? So by putting that capacitor in the feedback path, we've just created an integrator. That's all we've done. A very simple integrator. There is some gain associated with it though, right? Because let me redraw this. A closed loop. I have my integrator part here. This is not necessarily 1, right? So it's going to invert because of the negative sign. But this R1 times C may or may not necessarily have a gain of 1. So what you can do is you can pick C equal to 1 microfarad. What would the Rn need to be equal to? 1 meg, right? 1 times 10 to the minus 6 and 1 times 10 to the 6, they'll cancel each other out, and you end up with a gain of 1. So you can build a real-world integrator just by, picking your R's and your C's properly. Except you can't. Remember how we said in an ideal integrator, what was the gain? Infinite? It ain't really infinite, is it? There actually has to be a small voltage difference there to make this work. And I don't know if John talked to you about this. In real-world op amps, you always have some small, 10 millivolts DC between those two terminals, right? It's going to be small. There's some DC offset. So there's a way you can put a compensating resistor. You can drive those. Am I talking about this stuff? John hasn't mentioned it. Compensation resistors to get rid of DC offset. Well, oops. Kind of a problem if it's an integrator, right? Because you're always going to have a non-zero value here, which means you're always going to be feeding electrons into there until it saturates, correct? So this is an integrator, but it doesn't work for real-world op amps because it's always going to have some DC offset that's going to feed that capacitor. So the question is, how do you actually fix that problem? How do you make it an integrator that works? Add another capacitor? You would usually put a compensating resistor in one of the terminals. I can't remember which one it is, but it's usually an R sub C, and I don't know. You have to adjust it to get the DC offset to go very small. They do make fancier ones called chopper stabilized op amps that actually will automatically adjust their parameters to get it to be 0, but those are pretty hard to find. What would you do in the real world if you're not going to be sitting there tweaking your compensating resistor? What does the capacitor do again? Stores voltage. Somebody also talked about it being a filter at one point. So what does a capacitor do to high frequency stuff? It lets it through, right? What does it do to low frequency stuff? Filters it out, right? So this is going to store the DC no matter what. So what you need to do is actually put a resistor in parallel with it so all the DC stuff goes through here and all the frequency goes through here. So you have to put a real-world integrator which basically has this additional R value here, which is going to shunt off that value. And how do you do that again? Do you remember? How do you size this resistor? Did John talk about break frequencies and all that stuff? No? What's the definition of a break frequency or cutoff frequency? There's another term for it called the half power frequency. Half power means when 1/2 the power goes here and the other half goes here. How do you make 1/2 the power go through each element?
Just need to match the impedances.
You make R equal Z, right? Whatever the capacitance of the Z is. So whenever you have those to be in half the current's going to go through one, the other half is going to go through the other one. So R equals 1 over 2 pi FC. You'll know the break frequency that you want it to be, 10 whatever, 10 hertz, 10,000 hertz. You'll have a nominal size of your capacitor. You can size this resistor based on that break frequency. So to build a real-world integrator, you just put this other resistor in parallel with it, and then you'll shunt off DC. But this is actually a real-world integrator that can only integrate AC, right? It's an AC integrator. We can't integrate DC because what are we going to do? We got to get rid of the DC because the DC offset is going to cause that inverter to saturate every time. So, a little bit of interesting stuff, hopefully. Questions on that? That's how you build an AC grenade. Does John talk about this at all? I'm just asking because I know some people take 342 and because he talks about frequency response, right? For op amps and for circuits, but he doesn't actually talk about how to. Okay. You did go over integrators, but did he cover?
I don't think we did.
You don't. Oh, okay. That's okay. It's just good practice, right? Sometimes you see it a couple times or not, and it works from there.
I don't think you did. You can go back to like
Go back to where?
when you were the drawing and you were just
I'll try.
the AC into.
That's the AC integrator. And I will tell you why this is important, because I'm getting old. I guess you're only as old as you feel, but back in 1997 or 98, when I took the PE, I actually had a bunch of test problems on the PE exam that actually just had a bunch of op-amp circuits set up, and they had this device. So they had this set up like this. This is plus minus. They had an RI, and then they had a box over here that had some sort of VI characteristic, and that was their challenging problem, was to just make this so that you just had to look at a graph to figure out what the current flows was. This was a really super simple problem if you just use this basic concept of what can go into the amplifier, what doesn't go in, how does it pass through, and you just had to look at currents and voltages, and it was a super easy problem on the PE exam. So they thought they were going to really throw us for a loop, and it was a pretty simple problem. I passed the test for what it's worth, but that was the only problem I can remember. Yeah, congratulations, right? You all should be thinking about taking this too, right, next semester. That's the FE at least. That's the plan, yeah, it's good stuff. Because this is the type of stuff you can, if you just know a couple things about op amps, it's not a really difficult topic to understand. It's just, look at the current flows. And that's the other thing I hope that's cool about this class is you just see, oh, well, it has to go here because the current is 0. So maybe John does it that way, maybe he doesn't. So what we're trying to do is just say generically, where does current go? As opposed to, well, Kirchhoff says, blah, blah, you know what I mean? You get all into these procedures and approach. Well, it can current go? You know it can't go here. It's got to go someplace. So you can look at it somewhat intuitively, hopefully. Anyways, let's continue on. Try to straighten it out a bit here. Hold on. So that's our approach. Now, let me zoom down just a little bit. We did it for a bunch of op amps. Anybody want a little homework problem? Simple one? All right. Let's switch it up. Tell me what the transfer function of this is. The A closed loop. What is A closed loop going to be for this system? Is that a resistor? Yep, RF is the feedback resistor. This is your capacitor on that connects to your input. Your output is V out. I can zoom in a little more, make it more legible. How's that? Just a little practice. How am I doing for time? Plenty of time, okay. All right, any questions?
What's defined with that? Just
ACL, A closed loop, which is also going to be equal to my transfer function. A closed loop is the definition of the transfer function because it transfers the input to the output. That is the definition of a transfer function. So the closed loop gain is that. Could I ask you for A open loop? No? No, with any op amp you have an open loop gain, you have to have open loop gain. What is A open loop? I think Andrew said it. Infinite gain. For an ideal. In a 741, anybody look at the data sheets? What is it supposed to be? I think it's 200K at least, right? Is that right? Going from way back, pulling out the memory. You guys did labs, so we looked at data sheets for 741s, correct? And I think that they tend to be very high gains. Those are pretty cheap, inexpensive ones. I think really high precision ones, they tend to have much lower gain values. But I don't know. I've never really delved into that. That's not really my thing. Would be interesting. Does anybody know who Macintosh is?
You mean like
The audio company? Exactly. They make pretty nice op amps. I mean amplifiers. They are in New York. And just to see what type of equipment they use, worth calling and seeing, hey, I'm a college student. Can you tell us what kind of amplifiers you use in your stuff? And actually to get a tour there would be really, take a tour and come home with a couple of amplifiers. I wonder if they would notice. But they also weigh like 80 pounds because they use so much magnetics. So they're pretty good, but that's a dream. That dream went out the door whenever I had kids. Nice things do not exist when you have kids. Because I thought about buying one of these bookshelf ones. It was like, I don't know, $4,000. And the 30th time yesterday, my youngest kid was hitting a wall with a pair of tongs that we were playing around with. Just, you know, the walls are trashed, the floors are trashed, we're trashed. It's like nothing's in good shape. If you see our cars, I mean, there's boots and just food dropped, and you just like, at some point you sort of, I think crying uncle is the right expression. So, but they're worth it. As some of you can attest to, right? Who've been there, done that. All right, so now we've done some circuit analysis. We got a homework problem to practice it. So hopefully what you can do, and actually I talked about that on that PE exam, but also when I interviewed for a company in Washington, D.C., that was one of the questions they asked me, which is an RLC circuit. Can you write a transfer function for output to input? And I think I did okay on it because I started to do it in Laplace, and he didn't want me to do it in Laplace. He wanted me to write the differential equation, and I asked him, I said, but why? This is what we do as engineers. It's much easier to do it this way. And he looked at me sort of startled that I would actually challenge him to say, you know, I got the job, but still, he was like, why would you ask me? Because I think I flipped his thinking. Sometimes engineers, we get set in our ways. We always have to do it this way. It's like, no, why not try this easier, more efficient way to do things? And again, they offered me the job. They must have told me, like, yeah, he was doing it the wrong ways. Well, I basically said, you know, but it doesn't make sense to do differential equations because that's not what engineers do. I mean, that's, you know, look at any modeling book. But he went to Rice, and he was quite a bit older than me, and he might have done everything with who knows what. So anyway, let's continue. So let's just say that we have a bunch of different differential equations. Somebody has figured it out. It could be us, because we're circuit analysis pros at this point, right? We're good at it. It could be our friends in mechanical or chemical engineering who figured out a process to how to model it. It could be, you know, any discipline, right? Civil engineers, they may be doing some modeling. I don't necessarily know 100%, but all the disciplines have a ton of work to go ahead and come up with equivalent models of real-world elements. And so ultimately, they're going to come up with some equations that kind of look like this. You've got some derivatives, some nth order derivatives, all the way down to no derivatives. And then we have some m-order derivatives all the way down to no derivatives. And if we have to skip an element, it's no big deal. what we've hopefully learned in this class is we don't want to do any of these derivatives. We're going to take these to Laplace. So the very first thing we're going to do is bring that to the Laplace domain. So if this is an nth order derivative, then we just multiply by s to the n power, right? And all the way down until we've got no more derivatives, so that's just s to the 0, which means it's 1. So that's why we have a0 c of s. But if you recall, we have this c of t initial condition, so that could be c of 0, c is 0 prime, on and on and on, until we get to however our derivatives. And we do the same thing for our b side, right, or our r side plus whatever any initial conditions are. Okay? To do a transfer function, we're going to write it as c over r. And this is just for some reason some classical response or classical writing. So this is the input and this is the output. That's the v out over v in essentially. So c is our output and r is our input. If we want to do a transfer function, okay, here's the key thing. We can't form this equation with a bunch of initial conditions. So all these initial conditions can't be included, which means to do transfer function approaches, you have to assume that your system has no initial conditions, which is not always a big problem, because remember back from chapter 6, we would always do a 0 plus to infinity. So we would add on whatever, let's say, c initial conditions are. What we could do is we could just move our time. So let's say that our time started here and we had some initial conditions. We could just cheat a little bit and then say that our time actually started before when we started charging the system. So the way to make it work is you can actually just go back in time and let that be your starting point of 0. So don't start it right now, your analysis. Start it when you actually started getting some initial conditions. So that's the way that you can sneakily work around it. It's just to get rid of your initial conditions just by starting your time a little bit earlier. And that's my transfer function. My transfer function is g of s, and it has all the b's in the numerator and all the a's in the denominator. And our input is r, and our output is c. One key thing here to make our approaches work, and we haven't talked about that, s to the n had better be a greater power than s to the m. So a better way to say that is the order of the numerator is less than the order of the denominator. So n has to be greater than m. If m is greater or than or equal to n, we have to do some additional work. We have to do some long division essentially to do that, which means we have some impulse functions in our outputs, yada, yada, yada. So all systems, real-world systems, you should always have it that your order of your denominator is going to be greater than the order of the numerator. All right? So let's take a look at an example. Let's find some transfer functions for this circuit, okay? So the first thing we're going to do is we have to determine what our input is and what our output is and what our transfer function is. So our transfer function is transferring the input, in this case V in, to the output, V out. Because we have a 10 nanofarad capacitor in there, it would be easiest to do the transfer function in the Laplace domain. So we convert everything into the Laplace domain as so. Now, is there an easy way to solve for V out as a function of V in to get the transfer function? Is there any circuit tool that you've used in the past that efficiently will calculate what V out is given V in? Anything look familiar? I have a voltage across two elements which are in series with each other. Voltage divider, very good. So if I can use voltage divider, I can actually solve for V out over V in. So voltage divider tells me that V out of S is going to be equal to V in of S. What's the equation for voltage divider again? Do you recall? The one of interest, 1K, divided by the sum, 1K plus 1 over 1, 10 nano times S, and you're done. Okay? So our transfer function, V out over V in, this is just in the Laplace domain, is equal to 1k over 1k plus 1 over 1 times 10 nano, or 10 to the minus 9, s. Is this okay to work with? It's a pretty ugly looking fraction to work with, right? So let's make a little bit of the math easier. Let's multiply numerator and denominator by 10 nano times s. 10 nano, or 1 times 10 nano, no, actually it's just 10 nano, is 10 times 10 to the minus 9th, which is 1 times 10 to the minus 8th, right? What is 1k times 10 nano equal to? Yeah, because it's 1 times 10 to the minus 3, 10 to the positive 3, right? Times 1 times 10 to the minus 8th. What does that equal? 10 to the minus 5th. When you have them raised to the same power, you just add these two together. So 1 times 10 to the minus 5 is how you do that. So this becomes 10 micro over 10 micro. Whoops, I got to have the s term here, right? Plus 1, correct? Is this what I want it to look like? Does this look like close to the table? No, right? Because what should be multiplying s? This should just be a 1, correct? So what do I need to do to get a 1 there? Multiply by 10 micro over 10 micro, or 10 to the 6 actually, right? Or 10 to the 5th, 10 to the 6th. Or I can factor it out. So I have s over s plus 1 over 10 micro. What's that equal to? Right, because if it's 10 to the minus, 1 times 10 to the minus 5th, or 10 to the minus 6, I can just bring that around, and I get 10 to the positive 5th. So this is my transfer function for V out over V in for this RC circuit. Questions on that?
Yeah. Wouldn't it be 10 to the negative 11? Because which one would you know to make a positive when you're adding them together?
I'm adding them together. Hold on, let me give it a little more room so I can expand. So let's put this back up here and let's make it a little bit bigger. Okay, we'll start with that.
Well, they're both negatives, right?
They're both negatives. This right here is 10 times 10 to the minus 6s over 10 times 10 to the minus 6s plus 1. Is that what you're saying?
No, before when you get 1 times 10 to the negative 5.
This is 1 times 10 to the positive 3, because kilo is 3, right?
Sorry.
That's okay. Because kilo is 3, so positive 3 minus 8 is negative 5. But since we have it out here, let's just do it. We're going to factor out 10 to the minus 6 out of the numerator and denominator. Oops, I factored that out, so I don't need that there. So this is s plus 1 over 10 times 10 to the minus 6, which that's equal to, these cancel each other out, so that's s over s plus 1 over 1 times 10 to the minus 5th. If I have a minus 5 in the denominator, I can bring that up to the numerator, to the positive 5th there. Okay? Make sense? How to do transfer functions? A lot of this is just the algebra. We do a lot of it. Pausing for questions.
So then from there, would you do a Laplace transformation back to the time domain?
Excellent question. So the question is, do we actually transfer it back to the Laplace domain? And the answer is no. Why? Why don't we transfer it back into the Laplace domain? Because I have no idea what this input is. It is unknown. So I can't solve for v out of t until I know what v in of t is. And since we've already said it's way easier to work with v in of s to get v out of s, I have to know what that is first. That gives me that, and then I run it through my transfer function to give me v out, and then I go back and actually get v out of t. So here's the thing to highlight, right? You should never go back into the time domain with your transfer function because it doesn't really tell you anything. It might tell you the general response of the system, you know, how fast it responds, how slow it responds, but it doesn't tell you anything other than that. Okay? It tells you its natural system response, but it doesn't tell you the force response. So you should never, ever, ever go back into the time domain with your transfer function because it doesn't tell you anything. You can look at the roots and see how fast it's going to respond, but that's all it'll tell you. It won't really tell you anything beyond that. Good question. And there you have it. All that work sort of redone. Should we do another one? Do you rather just follow along in the notes, or do you like me chicken scratching away? Chicken scratching? All right. I will keep chicken scratching. So we want to go ahead and get a transfer function, which is v out of s over v in of s, which is going to be our gain of our system, our a, or our transfer function. And in control systems, I always call this g of s, which is our transfer function. So the question is there an equation or an approach to very quickly give us v out of s given v in of s? What is it? Well, KVL gives us, we get currents, right? We're just trying to get voltages. Yeah, do voltage divider rule again, right? If we do voltage divider rule, what we have is V out is going to be equal to V in times 0.1s over 10K plus 0.1s. So V out over V in. I'm going to factor out a 0.1 here. So I have S. When I factor out a 0.1, what does that do to my 10K? What is it? When I factor out 0.1 from 10K, it's dividing by 0.1, isn't it? So I actually get 100K when I factor it out. If you ever get stuck, right, just say I'm factoring out a 0.1, then you can see it that way pretty quickly. So I have 10K over 0.1, which is 100K, multiplying by 10. And that is your transfer function. Questions? So notice I said here, it says it simplifies determining inverse Laplace transforms, but that doesn't mean I actually take the inverse Laplace transform. Once I know what the input signal is, then I'm going to go ahead and do the Laplace transforms. So if I've already got this one factored down into just about ready to go for final form, then I just multiply my input, whatever that is, of S by S over S plus 10K, or 100K, sorry. And now I can just do partial fraction expansion because this one's already set up. I might have to factor this one to get it to look like something in the table, but it shouldn't be too bad to get from point A to point B. So that's why, as much as you can, you do it. All right, any questions? No questions? All right, let's do one now that is any completely random system. We have no idea what this system is. It could be a circuit, it could be a pump, it could be a process, it could be some sort of biological system. Who knows? We don't care. But somebody, probably smarter than us, gave us a differential equation that we need to solve for. So anybody want to solve this MAT 258 style without Laplace? No, I can't do it. I can do first order ones pretty easily, but I can't do, that's it. I stumble at first order system. I took a lot of math. It's just I don't use it. So, but Laplace, I can do algebra because we do a lot of that. So all we need to do is take this entire set of equations, this entire equation, and convert it to the Laplace domain, which means I'm taking the triple derivative, second, first, none, and then second, first, and none. So to do my triple derivative, I've got s cubed multiplied by cs, and I'm being 100% complete. I have to subtract s squared times c double prime of 0 minus s times c prime of 0 minus c of 0. That's my triple derivative. Then here's my double or second derivative. Here's the first derivative, and here's my final non-derivative term. And then I do the same thing for the other side. This is my second derivative, first derivative, and then this is the regular term. So first thing I'm going to do, any initial conditions I throw away. Okay? Initial condition means if I evaluate at a term of 0 in there, that is some sort of initial condition. So bye-bye, 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 goodbye, 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 and goodbye. So what I'm left with is s cubed c of s plus 3s squared c of s, and I got to start putting in little hooks to show that it's a c, plus 7s c of s minus 5 c of s is going to be equal to s squared r of s plus 4s r of s plus 3 r of s. That is my equation written just a little bit cleaner.
I don't think it's supposed to be -5 c, is it?
Is it plus? Yes, plus. Thank you. Oh. Okay, so now it would behoove us to go ahead and factor out the c's and the r's to get a simpler equation, because again, I'm looking for something for a transfer function, which is output over input, right? Which is c of s over r of s. So let's factor out my c of s on this side. And I have s cubed plus 3s squared plus 7s plus 5. That's on the left-hand side. That's going to be equal to, that was weird, r of s times s squared plus 4s plus 3. And my transfer function is output over input. It is c of s over r of s. Now I just have to do factoring, essentially, right? Not factoring, but dividing it out. And there you go. In this case, it would be helpful if you could factor that out, but anything beyond a second order system, right? You almost have to use a calculator. Unless, did anybody teach you any tricks in your math classes to get a third order to how to factor it? Just trial and error? What's that?
Synthetic division, would that work?
Well, synthetic division would work to do the whole thing, but I'm just trying to get this one in roots. So I need to evaluate it for 0. So I don't know any, I wasn't taught any way that I can recall to do that. But in your calculators or MATLAB, you can use CSolve, or I think in MATLAB there's a function called roots, and you just enter in the equation and it'll spit out the terms. If you use solve in your TI, that just does it for systems that does not have complex roots. If it's CSolve, if you do have complex roots, it'll do it and solve for it that way. I always recommend just using CSolve, because if you do have complex roots, it can handle it pretty easily. There is your system, written as a transfer function. Okay? Questions on that? Any questions on transfer functions? How to solve for them? Because you'll be doing this not too much more in this class, because what, we got 3 weeks to go in this class or something like that? So we're sort of limited in the amount of time that we have, but in the follow-on class, you almost always are just given a set of equations that you need to solve for. So you just solve the set of equations, and you just do it by a bunch of variables. Same thing in industry. A lot of times you won't be modeling the systems, somebody will actually do it for you. I have seen, and I've never actually had the opportunity, but there are companies that actually can give you models of systems. And what they do is they'll go to a plant and they'll do something that's called a bump test. They'll literally do a bump test, which means let's get the system to be stable. Let's say the process set point is, let's say, 30%. You want 30% of the process to be doing something. And then a bump test is you say, I want to go 30% instantaneously to a new value. Let's say 40%. So you bump it, instantaneous change. So a bump is when you go like this. And the idea, I guess, is if you're walking along a table and you hit it with your hip, and then the whole table moves really quickly, that would be a bump. So here's the input. It goes from here to here. And then you watch the output and see how the system responds. And depending how that system responds, you're monitoring this, right? You're monitoring time and then whatever the values are doing. So let's say you're trying to monitor position. What would you do? This is an equation, isn't it? In Excel, you can have Excel solve for an equation that will model this. I think Excel can do up to a seventh order equation that can replicate the function. So Excel can actually calculate what the function needs to be to do that. So these programs or these systems called ProTuner, all that stuff, that's essentially what they do. They bump it and they just monitor the time and the output, and they can give you a pretty good representation of the system. So if you can't or don't want to actually come up with a process, you can actually do that pretty efficiently. So I've actually only seen the results of it done once. The only time I've ever been involved in modeling a process that was not an electrical system is I worked at a nuclear power plant in New Jersey. Actually, it was in Delaware, but it was the only way you could get to it was New Jersey unless you swam or took a boat. But the idea was this plant had what's called a moisture separator reheater, and I had to design a control system that would control the heating up of the temperature, so opening valves and making sure that the temperature didn't go too high. Well, the problem is this system was designed in the 70s and there was no data, and so I was involved with developing a first order model of this massive moisture separator reheater system so that I could come up with a tuning constant so that it would heat up slowly and not overheat the system, because if it overheat, it went into alarm and then it would trip into manual mode, and then you had to kind of have the operators do it manually. So that was one of my proudest moments, because I had to work on Easter, and the operators in the control room, I think I told the story, but they warned me, don't go above 50% power. And how do you increase a nuclear reactor power? You just drop the temperature, which means you pull more steam out, which is if I kept cracking open the moisture separator valves, it could potentially have gone over 50%. And so the operators were yelling at me, you better not go over 50% power. And I'm looking at them saying, how do I know if it's going to go over 50%? I have no idea what it was. But anyway, it didn't go over that. But then there were two, because there's a plant, there's Salem 1 and Salem 2. And Salem 1 was designed by the engineer who worked there, and she had spent all this time taking modules from the Unit 2 and then putting them in Unit 1 to get a working system that was original. But she calibrated everything, and she did all this stuff and whatever. And she put her system into automatic, and it tripped onto manual mode. It wouldn't stay in automatic. And when they put mine in automatic mode, it stayed in. So they quickly replaced her system with my system. But at one point, I was the most knowledgeable person of that system. So that was one of my first, I think I was 2 years out of college, and that was my first system where I had to do that. It was a fun, if you get opportunities to do that, but it's pretty stressful because you're the only one and everybody's looking at you like you know the answer. And the worst part is they said, oh yeah, come up for a couple days and we'll help you out. Well, they wouldn't let me leave. They made me stay for 14 days. They said, no, you have to stay. And they were joking around, but they said, if you try to leave, we'll have the state police arrest you as you're going into Delaware. So I said, are you kidding me? And they kind of smiled and didn't say yes or no. So I said, I didn't take them up on that, but that was a pretty tough thing to explain to my wife, who I said, I'll be back on Wednesday, and 2 weeks later, I was back, so pretty stressful. Anyway, so now let's see how we can go ahead and expand this system to, we talked a little bit about it, a forced response system and a natural response system. So a forced response system is something you're putting energy in a system and you're forcing it to do that. So an example is if you have a car, for example, and some people check the operation of the suspension system. They'll push on it and they'll see the car rock, but eventually it kind of rocks and sort of steady state it's out, right? And it reaches the same level of height that it had before. So the natural response is you bumped it, right? We pushed it down or pulled it up, either one, and we saw how it rocked until it reached a nice stable operating point. Whereas in the case of a forced response is I bumped it, but then I kept leaning on it so that it achieves a new steady state position. So instead of the vehicle getting to a certain height, it's going to be at a lower height because I'm continuing to put energy into it, right? I'm continuing to push down. So the concept of a forced response is, what is your input? Is your input continuing to apply energy? So in the case of electric circuits, when we energize a circuit, will we keep the power supply on? Or will we just bump it? Do we energize it and take the power away? Or do we put that 12-volt DC system in and we keep it on for forever? That would be the forced response. The natural response is, I've got a bunch of R, L's, and C's in the system, and they're going to be absorbing energy and exchanging energy and dissipating energy sort of based on their natural, normal equations, and those are going to kind of dissipate out a little bit and then come up with a response. So remember in lab, when we actually looked at a system, one of them had a steady state value that was non-zero. That was the forced response. The other one was a zero response. That's because it just didn't store any energy anymore, so that became the case where that was kind of the forced response in that case was zero. But in both cases, they rang a little bit, right? There was some oscillatory response if it was in the underdamped case, and then it reached steady state. So the natural response is just how the circuit is set up. So if I have a transfer function that has a g of s, a y of s, and an x of s, this is the input, and this is going to determine the forced response. This is the system, and that is going to be the natural response. And then the output is the actual response. That's what you're monitoring. And it's going to be a combination of these two. How that system actually responds is dependent upon what we have for the x of s and for my g of s. Okay? So when I look at my system, this is s squared over s squared plus omega n squared. This is either a sine or a cosine wave, right? So the output has a sine or a cosine wave that is going to stay there, for forever. This one right here, most likely, but not guaranteed, most likely is going to have some ringing and decaying to a new value. All right? So here's our transfer function result, right? You can see that all of these are going to decay. E to the minus b, e to the minus d, e to the minus f. All those terms, as time increases, all those will go to zero. Do you see any exponential decay associated with that? Absolutely not. And so this one right here determines the system that has no exponential decay. These other terms are the ones that are going to decay with time. So this, again, just to sort of summarize, this is the natural or transient, sometimes you'll see. This is the forced. Sometimes it's also the steady state. You'll see those terms used interchangeably. Okay? So if I continue to energize a system, it's going to respond energize. There's only one type of system that does not. Do you remember in the case when we talked about second order systems? We have over, under, and critically damped. What if there's no damping? What if there's no resistance? Once you energize a system, an inductor and capacitor system, they're just going to keep exchanging energy back and forth, back and forth, back and forth for forever. And if there's no resistance in the system, there's no energy dissipation, which means you've energized it once, you go away. We talked a little bit about this in the class the other day. That's how we get an oscillator, right? It's something that rings and rings forever. So remember the Tacoma-Narrows Bridge? You probably saw that in physics class, where it just kind of, why was it swinging so easily when the wind speed was not too bad? It's because whatever the wind, however the wind speed was coming along, it was exciting it at its natural response. So there was very little damping at that specific frequency. So it would just swing back and forth without hardly any energy putting into the system. And then once the amplitude got so high, so it wasn't that the wind speed was picking up, it's just that maybe the amplitude, and I don't know, I can't exactly categorize because I don't know exactly, then it started to swing massively, and at some point it fatigued and broke, okay? So if you want to get something that's oscillating, you just energize it at one point, have no resistance, no dissipation, and it can potentially ring forever. The problem is you're never going to get R equal to 0. That just doesn't happen, ever, 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 ever. Okay? Any questions before we head out for the day? Because I think I'm just about out of time. Unless you want to try to jam in some poles and zeros. Because poles and zeros for the G of S, they really tell you where it's at. That will really help you when we cover poles and zeros of transfer functions. That's going to help you big time when you look at root locus plots for next semester. Okay? I talked about mantras in classes, so here's another mantra that'll help you next semester. You start at a pole and end at a 0. Start at a pole and end at a 0. That'll be a mantra to remember for next semester. All right, I think that I'm out of time, so have a great day.